enthalpy, we already mentioned what this is. Enthalpy is abbreviated with an H, and it is the potential energy for something. Really just the potential energy. And so it relates to the stability of an object. If you have an object with high enthalpy, it's very high in potential energy. It has the potential to undergo change readily, so it's very unstable. So enthalpy, if I have a high or large enthalpy, it's unstable. It has a high potential energy. Right? So if I have a molecule with an incomplete octet or lots of formal charge, it's going to be really unstable. It's going to have a lot of enthalpy. We can also think about enthalpy. Usually we think about enthalpy of the products versus enthalpy of reactants, right? If we're talking about a chemical change, like the example we talked about, where the hydrogen and the oxygen combine to make water. If we want to know how much potential energy this reaction could release, we would look at how much potential energy is stored on the reactant side versus how much potential energy is on the product side. Right? Because if I have a certain amount of potential energy stored here, and now later I have less, then that energy has to be released into the surrounding. And so since potential energy is the same as enthalpy, I'm looking at the combined enthalpy of the reactants and the combined enthalpy of the products. And so the change in enthalpy, or change in anything, delta anything, change in temperature, change in whatever, it's always final minus initial. So I'm looking at how much potential energy do I have in the end minus the amount of potential energy I started with. Right? So if I look at this specific reaction, I've got a high potential energy to start, right? Because those electrons are not held as close to the nuclei in the oxygen and the hydrogen as they are in the water. And I have a low potential energy. Water is very stable. The electrons are held very nicely to the oxygen nucleus, so those are really very stable bonds. So there's low potential for them to undergo changes if they're stable in that arrangement. So if I have a low and a high here, and I plug these in down in this equation, the products have a low potential energy. That's going to be a small number. And the high potential energy is going to be subtracted from that. So when I take the small number and subtract the larger number, I get a negative overall. Right? That means it's isothermic. Right? So that's confirming that the equation matches with what we said. When we have a reaction that has a lot of energy to begin with, but then the products have less, that energy is released into the surroundings. It's going out exothermic, and that's a negative sign from the point of view of the reaction. That's what we get when we use the formula properly. So if you can understand conceptually, that when the potential energy is going down, energy is released, and that's going to be negative, you don't really have to memorize that it's products minus reactants. If you subtract reactants minus products, you'll still get the same number, you'll just have the wrong sign. So if you ended up putting some numbers in here and you got a positive sign, and you say, wait a second, I know that this reaction should be releasing energy, I know the sign needs to be negative for the change in enthalpy, or delta H for the reaction. So here's an example. We already saw this. So if I take ice and I melt it to make liquid water, in this case what we saw in the video was we're only breaking bonds. So that's definitely going to be an increase in enthalpy. It's going to take a specific amount of energy, a specific amount of potential energy difference between the ice when I have all the H bonds formed between waters, and in the liquid when I only have some of the H bonds formed. Right? In the liquid, the molecules are still close together, and they can still hydrogen bond, but they're moving around more, they're sliding past one another. Maybe a given molecule of water only has 1 or 2 hydrogen bonds formed with a neighboring at any given moment on average. In the ice, the water molecules are three-dimensionally arranged in a crystal so that each water molecule has 4 hydrogen bonds three-dimensionally in space, and so I've got more attractions there. So I've got more attractions. The attractions are the same strength, but I've got more of them, and here I've got less. So anytime I can conceptually realize that I need to break attractions, I know that the potential energy has to go up. And so per mole of attractions, actually that's not quite correct, per mole of molecules, if I had Avogadro's number of water molecules in the form of ice, and I wanted to melt them, to break that number of attractions requires this specific quantity of energy. So the system is the water, the surroundings would be the table or the room, whatever, a hot plate or whatever I'm using to melt the ice. And so energy is going from the surroundings to the system to break those attractions. And so that's a positive change in enthalpy. An increase in potential energy is a positive change in enthalpy. And so that's endothermic. Anytime I break attractions, it's endothermic. Opposite example, here I've got the combustion of methane. So if I measure delta H, I get a negative value. When I plug it into the formula, that means that there's less potential energy in the products, more potential energy in the reactants. And this is trickier than just melting. It's trickier than just a physical change. It's trickier than just a change in state of matter, because in this case I'm not just breaking attractions or just forming attractions. In this case I have to break all the CH bonds, because there's none of those in the product. I have to break all the OO bonds, because there's none of those in the product. All of those breaking of bonds requires energy to be absorbed. So I have to absorb energy. There has to be strong collision. That energy has to be absorbed to break up all those attractions. But then, when I form the new attraction, since they're more stable, there's less potential energy here on the product side. And when I form those, a net overall quantity of energy will be released. So it's exothermic. So in this case, the system is the reaction. All the molecules involved in the reaction are part of the system. The surroundings might be the solvent, or it might be the house, if you're using this reaction to heat your house, or the furnace, or whatever. That energy has to be released, because now if I have stronger bonds, I have less potential energy. Energy can't just be destroyed and go into nothingness. It has to be there in one form or another, so it's released into the surroundings, and that's exothermic because energy is going out of the system. The system has less energy. So if I take a mole of methane and 2 moles of oxygen, and I make 1 mole of CO2 and 2 moles of water, this is the quantity of energy that will be released. Right, so really these are per mole of reaction. When you see delta H, it's not per mole of substance as much as it is per mole of reaction. Right? Because the system is the reaction. The system isn't just methane. The system is the reaction itself. So when I have a balanced reaction, if I do that reaction a mole of times, Avogadro's number of times, and it takes 1 mole of methane and 2 moles of oxygen, that is what I mean when I say per mole. If I do the reaction Avogadro's number of times, or per mole of reaction, that's the quantity of energy associated with that particular reaction. So there's some other, once I know that value, I know that it's proportional to the quantity of material as well. So that's what this slide is showing. So what we already saw, actually this is different. So if you recall, just mention that, if you recall on the last 2 slides ago, going from water solid to water liquid, that was 6.01 kilojoules per mole of reaction. And the reaction with 1 mole of water, it wasn't really a reaction, it was more of a process. But here, if I go from liquid to gas, the amount is 44. So why is this liquid to gas change so much greater than the solid to liquid change? Yeah, got to break a lot more bonds. Very good. So in the solid, as we said, the water molecules are packed in just right to form 4 hydrogen bonds per molecule. Right? So each water molecule has the capability of forming one hydrogen bond here, 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 and here. You can form 4 of those. So all the water molecules line up to form 4 hydrogen bonds. So if I want to melt this, I'll maybe have to break 1 or 2 of those on average. And the water molecules are still close enough together to form lots of hydrogen bonds together, but they're just moving a little bit, so they don't have as many hydrogen bonds. To go from a liquid then to a gas requires that all the hydrogen bonds be broken. All the remaining hydrogen bonds that weren't broken to go from liquid to solid have to be broken to get to the gas phase, because in the gas phase the particles are far apart, they're moving fast enough not to form any attractions. So that's why this number is so much larger. If I want to do the reaction and it's balanced 1-to-1, so if I do per reaction I have only 1 mole, then that's 44 kilojoules. If I throw different coefficients in here and it's still balanced, but I double the coefficients, now per mole of reaction, if I do the reaction 1 mole of times, the reaction requires 2 moles of water. So 1 mole of reaction would be 2 moles of water if I balance it this way. So in that case, per mole of reaction, that'd be twice as much water, so I'd have twice as much energy required to break all the bonds. Right? So if you change the coefficients by doubling them, then the energy associated with that process is going to be doubled. The state of matter in a reaction also affects the enthalpy of reaction. So this is one we just saw. When I do the combustion reaction, because the products are more stable and have less potential energy, there's a certain specific quantity, negative 802.4 kilojoules of energy released. If I do this reaction a mole of times, or Avogadro's number of times, how would I figure out how much energy is released if I just did one individual molecule of methane reacting with oxygen to produce these products? Well, this is the amount of energy per mole. That's a relationship. We're going to do some more conversions later today, but just to introduce that as a relationship, negative 802.4 kilojoules per mole of reaction. So that's per mole of reaction. If I don't actually have a mole of reaction, it's going to be a different number. If I have 2 moles of reaction, it's going to be twice that number. If instead of having a mole of reaction, I only have one single molecule reacting, then I know the relationship between a mole of something and one molecule. It's not a 1-to-1 relationship. It's Avogadro's number, 6.022 times 10 to the 23rd things per mole of those things. So in this particular example, I have one mole of the CH4 per mole of reaction as well. That's an important relationship there as well. Okay, so the way I set that up is I've got this relationship per mole of reaction, that's given. Then if I want to cancel the mole of reaction and get the mole of CH4, I have the balanced reaction. So in one reaction as it's balanced, I have one CH4. And so that's a 1-to-1 ratio. That's what I have here. I should have put that second. But then also per mole of CH4 molecules, it's Avogadro's number of individual molecules. So this is per mole of CH4 molecules. I have that many CH4 molecules. So if I then look at all the units canceling, if I want to know how much energy per individual molecule, I would have to take that number, negative 802.4, and divide by Avogadro's number. You get a tiny, tiny, tiny amount of energy per molecule. Right? So that's why that's not a... We don't usually talk about the amount of energy in a reaction related to how many molecules are reacting, because per molecule it's a really, really small number. We talk about it in relation to how many moles of reaction are happening. When you're in the lab, you usually have enough material that's somewhat close to a mole, so you can have a sense for how much energy will be released when you release that mole. So if I do this reaction, and instead of collecting the water as a gas, I cause the water to be condensed into a liquid and collected as a liquid, I can see that changes the amount of energy released. Why would the quantity of energy be released be greater when the water is in the liquid state rather than the gas state? Yeah, every time I form bonds, energy is released. Right? So for both of these, if I look at the reactant side, it's the same. I have to put the same amount of energy to break the bonds here up above as I do below. But on the product side, I'm forming the same chemicals, so I release the same amount of energy when the new covalent bonds form to make CO2 and water. But then, if I form liquid water compared to the gas, I'm having the gas water molecules that have formed and released energy come together and form some hydrogen bonds with one another. And that releases even more energy. So I can tell, based on the gas to liquid condensation, the amount of energy required for that, which we just saw in the last slide, for two molecules of water liquid to condense into 2 molecules of water gas would be associated with 88 kilojoules. So if I'm evaporating the gas, it has to absorb 88 kilojoules. If I take the gas and condense it back to a liquid, then it would have to release 88 kilojoules. That would be negative. It would be released. So that's what I'm talking about here. If I do this reaction, it releases a certain amount of energy. If I then take the water and condense it into a liquid, I form a few more hydrogen bond attractions. That's going to release 88 kilojoules more than I released initially when the water was in the form of the gas. So that's why the difference here is 88 kilojoules per mole less, because that's the amount of energy associated with condensing 2 moles of water gas into 2 moles of water liquid. And so this is what we already saw, this first one. So that doubling the coefficients goes for any reaction. If I take the coefficients, have a certain amount of energy associated with that. If I double all the coefficients, I'm going to double the amount of energy associated with it. Also, if I reverse a reaction, I have the same amount of energy, just the opposite sign, right? That's the law of conservation of energy. So if I do the reaction between oxygen and methane and make CO2 and water, that's a lot more stable. So the bonds release energy when they're formed. But then if I take those bonds and I have to put energy in to break them, it's going to take a lot of energy to break them. And then when the new bonds are weaker, they don't release as much. So in that case, I have a net absorbance of energy for the reaction, has to absorb that energy for the reaction to occur. So if you flip a reaction, you look at it in the opposite direction, the energy associated with that will be opposite, equal, but of the opposite sign from the other reaction. All right, so let's look at this conversion here. So here I've got a specific reaction, and this is the reaction that takes place in plants. Plants use the sunlight as their energy source. So they take sunlight, and the energy associated with that sunlight, they convert it to potential energy to run this photosynthesis reaction. That converts water and CO2 from the atmosphere into sugar, in this case glucose, and oxygen. That's why plants release oxygen, right? But the glucose and the oxygen are less stable than CO2 and water. So in order for plants to do that, it's an endothermic reaction. They need energy to put in to do that. And they get that energy from the sun. If you measure the quantity, it comes out to be this quantity per mole of photosynthesis reaction. So that's a relationship. That means that 2803 kilojoules equals 1 mole of reaction. So the question here is, how much energy is required? How many kilojoules do I need if the plants are going to make 75 grams of glucose? This is why the conversion approach to solving problems is so great, because we can apply it to almost any chapter in the textbook, no matter what the context of our problems are. So what other relationships do I need here? Yeah, I need moles to grams because I've got grams of one substance, and I want to know how much energy is associated with that. The relationship I have for energy is between energy and moles of a reaction, which the reaction is not the same exact substance as the C6H12O6. So if I have information about one substance, I want information about a different substance, I've got to convert to moles first. So 1 mole of C6H12O6 is equal to the number of grams I would get if I add all those masses on the periodic table. So 6 times 12.01 plus 12 times 1.008 plus 6 times 16 gives me 180.16 grams. So I can use that. Now I've got moles of glucose, but the relationship I have for energy is between energy and moles of reaction, which is not the same as moles of glucose. In this particular reaction, it happens to be the same because the coefficient here is a 1. But if I had any other coefficient here in this balanced reaction, I can't treat moles of reaction the same as I treat moles of a substance in the reaction. So I really need that relationship. So for every 1 mole, because it is a 1, make that red to highlight that, for every 1 mole of C6H12O6, that is the number of that substance for every one time I do the reaction. Then I can apply this relationship for every 1 mole of reaction. It's 2803 kilojoules. So now I've got the unit I want. So I just need to plug all that in. 75 divided by the molar mass times 2,803. And I get, with 3 sig figs, 1.17 times 10 to the third kilojoules.